and the attacker won't get access to all the other functionalities or interfaces inside DOM0, so that they can't do anything to harm the host or the whole system. That's a nice feature, yeah. This doesn't sound right. Yeah, I got distracted. I forgot about what I'm going to say. All right, yeah, and QEMU subdomain. Currently, we only have QEMU traditional subdomain, which is based on the QEMU 0.11 fork inside Zen, and is so this work is about how to make the QEMU upstream subdomain, which you will pull directly from the upstream QEMU tree and build a subdomain out of it, and then you can just use it to serve a guest. Yeah, so let's get started. So I've been working on this project on and off for the past few months, but unfortunately I was quite overwhelmed by all my other duties, so I didn't really get to the point that I can boot the subdomain with this. But yeah, I'll try to present what I have by now anyway. So here's the agenda. First, I'd like to give a little background information on the whole project, and then give a very short introduction to the Rump kernel, and then give the reason why we choose Rump kernel and compare it with other solutions we considered. And then we go more specific about what are required to build a QEMU upstream subdomain. And finally, give some very brief status report about this project. And feel free to interrupt me anytime if you have questions. So the background is that, as I said just at the beginning, currently we only have QEMU traditional subdomain, and it would be very nice if we have QEMU upstream subdomain as well, so that we can have feature parity with our own fork of QEMU, and finally get rid of that fork forever for good reason, and use upstream QEMU for everything. Currently, we can't, just because, well, we don't have QEMU upstream subdomain now. And because the QEMU traditional fork is now in maintenance mode, is causing some problem for us. For example, so there were some patches to patch XXA in a QEMU emulation code, which we don't have time to apply for the traditional subdomain. But fortunately, a member of the community posted some patches to fix that. But in the end, well, we need to get rid of that so that we can reduce our maintenance burdens, and also probably help our users to just use one device model to make their life easier. And the QEMU subdomain, as far as I can tell, is the most secure option for sandboxing QEMU. Well, don't get me wrong, QEMU is a great project. We still need that. We need the emulation code. But, well, there have been, well, people seem to be quite interested in QEMU security these days, and there have been many bugs discovered during the last few months. So we eventually, we do want to provide several levels of sandboxing mechanisms to do that. For example, there are ongoing work to use some specific hypercode to restrict QEMU, and also to run QEMU as non-root user in DOM0. But those are, there are trade-offs. So the most secure option is to use subdomain to just sandbox the whole QEMU process, so that it can't interfere with, it doesn't reside in DOM0. It can't interfere with, or mess up with all the other interfaces at all. But be aware that there are downsides. Otherwise, people would just use that all the time, of course. Because if you run it in a QEMU subdom, you do actually need to allocate some extra resources for that. And it also sometimes it makes it harder for service provider to model their product because, well, sometimes you need to know the implication of scheduling and the implication of resources requirements. And that also means maybe some extra resources make them harder to run more guests so that they can't make the same amount of profits as before. Yeah, so there's no perfect solutions to this problem, to the QEMU security problem. So there are definitely trade-offs. So just be aware of that. And then here is the introduction to Rump Kernel, which I shamelessly steal the picture from Anti's blog post on blog.zen.org. So if you're interested in knowing more about Rump Kernel and unikernel, go to blog.zenproject.org and look at Anti's blog post. It is a very good post, and it's a good summary about the Rump kernel and Rump run based unikernel. So yeah. So basically, there's the concept of unikernel and Rump kernel that you extract any components in the kernel you like and connect them or tie them together as you need, as you see fit, and then link them with the underlying platform specific code to build a unique kernel. So strictly speaking, what in this talk I'm referring to this Rump run unikernel. QEMU is the application in this graph, and the libc TCP/IP stack, or the other protocol stack are all based on this Rump kernel. And then there's some platform-specific code which are specific to Zen, which is now also in upstream Rump kernel. I'll get into that later. So any question about this picture in this graph? Okay. So yeah, I guess it's very clear here. And to build an QEMU upstream stub domain, we've considered some other options as well. So far, we consider 4 options. The first one is to roll our own. The second one is to make it based on Linux. The third one is based on OSV. And the fourth one is to base on Rump kernel. So what about rolling our own solutions from scratch? That's basically the solution, the route we took for QEMU traditional Stubdom. In QEMU traditional Stubdom, we basically took mini-OS, which was designed to be a minimum PV guest for demonstrating and teaching purpose, and put a libc on top of it, and then add in a bunch of hacks to provide some POSIC interface, like some API calls and some pseudo device like tab interface, and then we put some more hacks into QEMU traditional, the fork we have, to hook it up to all those pieces of code. And then we have some other code in our two-stack controlling library to hook it up into mini-OS. And then, well, this pile of messy code, and then we pull them together and compile it into a domain, an image, a kernel that can be built by the Zen two-stack. Yeah, to be honest, this is not very nice. And at one time, I have already split the mini-OS out of Zen 3 so that you can use it to whatever you want. But at one time, I tried to make sense of the Stubdom makefile and build system. And whenever I touch it, it breaks in 1,000 ways that I don't know how to fix. It's in a quite miserable state. So in the end, well, the conclusion is that this kind of rolling out our own solution would require too much work to maintain. And then because QEMU upstream changes a lot, sometimes it requires a bunch of, as it goes along, it requires more and more library to build. Something used to be optional now becomes mandatory, and then maybe the library use some specific system interface and this and that. We really can't write those codes all along. So this is not a very sustainable solution. And then the next solution we consider is the Linux-based solution. Actually, well, this idea is not that new. So Anthony Perrott, my colleague, who built a prototype years ago, and people seem to still be interested in that. And one guy, reposted that patch series some times ago, but unfortunately it didn't go anywhere because of many issues. For example, the most, the unsolvable problems to me is that it's still very hard to build the whole thing. For example, to make a Linux-based Stubdom, you need to first get a kernel that's working, Linux kernel that's working, and then you need a bunch of script to extract all the necessary library that QEMU depends on, and then put it into and bake an image, and this image with those libraries, and then put in an init script, or currently people like to use systemd, or put in a systemd unit file to bootstrap the domain, service domain, into a specific state. And then finally, you can put in the QEMU process and start QEMU from there. So currently, I don't know whether any of you have ever looked at that patch set. Most of them were about, well, scripts, how to extract things, how to analyze what libraries QEMU depends on, and how to extract things, and how to build Linux kernel. And then there are some other patches, a little bit, a few lines of patches to QEMU to patch it to start in that specific mode. Yeah, it's a lot nicer than this rolling our own solution, but it still requires a lot of work to maintain this whole thing. And because we, as an upstream, is not a distributor of binaries, so we can't actually work out a solution for our users to use this kind of thing. We can't just, we can't just ship a script and say we'll use that script and build this and build that. Apparently, it's very easy to break on different systems. For example, the original patch set used a tool called DragCut. I think it's only available on Fedora or something. Maybe there's a package on Debian as well. But Debian definitely doesn't use that to bootstrap a system or debootstrap a system. So we either need to maintain this whole script for every single distros in the world, or we need to invent some, we need to write distro-specific building script for every distros in the world. Of course, this is not very sustainable going forward. Right, so in the end, this work is kind of stalled and didn't go anywhere. And then there's the OSV-based solution. So do all of you know what OSV is? No? So it's sort of like, how to say, maybe I should just open their homepage for you. Right. The operating system design for the kernel. It's sort of like another unit kernel solution, but started with KVM support in the first place. They also provide tool chains to change to build your application into an VM. Yeah. So at the time I look at it, it doesn't have PV support. I didn't have PV support, and yesterday I checked, it still doesn't have PV support. So that means we can't actually use it. Why? Because the reason that we use QEMU Stubdom in the first place is that we need to contain the vulnerability inside the service domain itself. So if you use if we use an HVM domain, that means we need another QEMU process in DOM0 to emulate other things for our service domain. That means whatever vulnerability is used to be used by the attacker to get into our service domain can use the same vulnerability to get into DOM0. So that's not not really a viable solution. Yeah, so I forgot to mention, this QEMU Stubdom currently has to be in a PV guest, because PV interface are much more restricted than the HVM interfaces, and it requires no emulation whatsoever. So we don't have yet another QEMU process in DOM0 to service the service domain itself. Okay, and the other thing we consider that broke the deal for us is that OSV was written in C++, and we didn't really have any expertise in C++. So yeah, in the end, sorry, there's no to that solution. And finally, there was this Rump kernel-based solution. Yeah, it's a bit like, a bit like OSV, because it provides a tool chain to turn your application into VMs, and the tool chain is getting better and better as we speak, basically, because so Martin, who sits there, has done a lot of work to make it look like a normal Unix tool chain, and so that basically every time I found a problem and I just sit around, and a few weeks later, oh, that problem is solved. Yeah, saved me lots of work. Thank you. And then this Rump kernel is based on NetBSD code base, is properly maintained, and it also makes available many NetBSD infrastructures so that I can directly use them. I don't need to write any code for it. And then the most important bit is that it provides some POSIX interfaces. It's not all POSIX interfaces. It doesn't provide all POSIX interfaces, such as signals and fork and this and that. But for building a QEMU subdomain, that's good enough. And then the most important bit is that it has PV support. Yeah, so that we don't. Well, that's basically all we need for that. Yeah. So what are actually required to build a QEMU upstream Stubdom? Or even if we can go further, just that what is required to build a service domain for Zen? Just not just QEMU. We can build any service any other service you would like to build that into a domain. Basically, we need Zen bus driver, which communicates with ZenStore, so that you can read from and write to ZenStore, exchange information with DOM0 and other domain. And then there's the priv command driver. So if you are building a service domain, you might want to map some pages in the guest, or do some other operations on behalf of the guest, or control the guest, so that you need a priv command driver, which is a driver used to issue hypercalls and map guest memories. And then the next thing is the ground table driver. This might be optional, because as a service domain, you already have the privilege to map arbitrary pages from that guest. but it would still be nice if you can cooperate with the guest, use the ground table mechanism to communicate. Well, and the next one is sort of QEMU Stubdom specific, because if you want to dump package from QEMU to the kernel, you need a tap device. And in the case of a normal service domain, not just a stub domain, for example, in Linux, you will also need bridge to bridge the tap device to a real Ethernet device or whatever devices that goes to the outer world. And then the final thing is that the communication channel between two-stat domain and QEMU, so that you can control the QEMU inside of DOM0. For example, you tell it, well, you need to dump the state to this place so that I can save this domain or migrate this domain to another places or change the internal emulation state. Yeah, so those are the basic requirements. And then how are they done in the QEMU traditional stub domain? Well, I think I've mentioned this before. So for various drivers, for example, this ZenBus driver, priv command driver, ground table driver, we had a bunch of code that hook directly up, hook in the libxc, make libxc hook up to the minios underlying hypercore interface. Yeah, that's not sustainable because that requires that makes it impossible to build the service domain out of Zen3. And for the tag device, it's also hacked together. It dumps traffic directly to the width. So when you say, for example, in QEMU, you say open tab, and the underlying code would just recognize that, oh, this guy wants a tab device. Then we run this code snip to make return a fake FD, and then sorry, okay. Right, sorry, yeah. And the communication is done via special consoles. And in the QEMU upstream start domain, all the drivers are now properly upstream in Rump Kernel, which means you can build this thing, build this unit kernel, solution, build whatever you need into QEMU completely out of Zen3. Just use their tools, that is good enough. And then the tap and bridge device are provided by NetBSD. What I did is just enable them and then make it compile and link them together. And the communication currently is still an open question. We use libvchan or TCP network. Yeah, so that's the status. There's really nothing much to say. I ran out of time. There are some problems needed to be solved, which I haven't got around to solve them. So how to bootstrap the Rump kernel to a certain state. There's no solutions yet. And then there's toolchain stuff and how to integrate with the recent project. Yeah, so because I've run out of time, I'm going to go into details. Right. Okay.
I was just going to ask, do you have kind of a wiki page or kind of a mailing list post that says where you want to go? And
yeah, I wrote a wiki page some time ago, but it's most of my brain dump. It's not very well organized, but I will try to write up something in the future.
So that others can.
Yeah, sure. Yeah.
Yeah, could you estimate how much memory such a domain would need?
So in QEMU traditional Stubdom, you normally allocate 30 megabytes of memory. I don't actually know how much the QEMU upstream Rump kernel would need, but I would say maybe 32 to 64 to be safe, right? Okay. If there's no other questions, let's call it a day. Yeah. Thank you.